Remember in the last two videos, the last two main videos, we talked about the OSI model and the TCP/IP model, and we talked about how the layers are separated and what are the functions of those specific layers. In this video, we will gonna focus on the network layer or the internet layer from the TCP/IP model. And to be more specific, at the network layer, we have the packet which is composed from the IPv4 header or IPv6 header and the payload. This should be the IP header. And this will gonna be the payload. The payload is the data which is coming from the layer above. We will gonna see what the IP header contains and what are the fields in the IP header, what are the functions of those fields, and with which purpose they were created. The Internet Protocol version 4, the one we will gonna talk about in this video, is one of the core protocols on which the internet was built on. The Internet Protocol is used in packet switched networks, and it is connectionless. That means that acknowledges every packet. It uses a 32-bit addressing system. The IPv4 addresses are made out of 4 octets. Please consider that 1 octet means actually 8 bits, or an octet you can also call it a byte. The IPv4 subnets are assigned only by IANA, and if you want to find more about IANA, you can find the link down below into the description. Regarding 32-bit addressing system, the IPv4 addresses and the IPv4 subnets, we will gonna talk about them in to the IP addressing video, which will gonna be a special one, and over there we will also learn how to convert from a binary to decimal and backwards. Going further to the main focus of this video, IPv4 header. You can see that it has 14 fields and only 13 are required. These options over here, they are not required, and only in case of the internet header length will have a value bigger than 5, then you can use the options. Over here you can see the 32-bit system that we will gonna use for explaining the bytes and their responsibilities. Our first field from the IPv4 header is the version, and considering that we are talking about the IPv4 header, this will have a value always equal to 4. The next one is the internet header length, which specifies how big or small the size of the header it actually is. It has 4 bits, as you can see here, and it contains the length of the header in 32-bit increments. The minimum length of an IP header is actually 20 bytes, and the maximum one is 24 bytes. So in this case, that means that the header length should contain either a value of 5 or 6. A much bigger field is the DSCP, or Differentiated Services Code Point, which is a 6-bit field. This one, it was originally called type of services field, and it got updated by IETF with DACP to allow for better classification options regarding the technologies which are requiring real data streaming. And for real data streaming, you actually have video or voice services. In this way, when you're doing a class of service or a quality of service, you can actually use this field to tell if a packet should have priority or it shouldn't. Now, the explicit congestion notification is a 2-bit field that allows end-to-end notification of network congestions without dropping any packets. This field is actually optional, and it will be used only when both of the end devices or endpoints they are capable and they want to use it. The total length field is 2 bytes long or 16 bits, and this one tells you how big is the entire packet. Please remember that the packet is the IPv4 header and the payload or the data which is coming from the transport layer, and this should have a minimum size of 20 bytes in case the data that came is empty, so that means the IPv4 header without any data, and the maximum value of the packet should be 65,535 bytes. The fragmentation in IPv4 header, it is done in the host or routers or firewalls, and the fields that will gonna tell us if the packet will gonna be fragmented are identification, flags, and the fragment offset. The identification field is used to identify a group of fragments from a single IP packet. The flags field is a pretty interesting one. From this field we have 3 bits, but actually in real life we will gonna use only 2. So let's start with bit 0. Its main purpose was to indicate packet has been sent with bad intention, so a computer can ignore any messages with that bit set to 1. But of course, come on, which hacker or which person which has bad intentions, he will gonna set that bit to 1. Moving on further, we will gonna talk about the do not fragment bit. If you have this bit set, it will not allow any kind of fragmentation. So for example, if you receive a packet that wants to be fragmented, the router which receives it, it will simply drop that packet. The do not fragment bit can also be used for path MTU discovery, or it can be automatically done by the host IP software or manual using diagnostic tools such as ping or traceroute, for example. But in case we would like to use fragmentation in a packet, we can set the multi-fragments bit to 1. So this will gonna have a value of 1, this will gonna have a value of 2, this will have a value of 0, of course, as we talked about. So if we will have these values, that means that we can fragment packets. The fragment offset field is made out of 13 bits, and it specifies the offset of a particular fragment which is relative to the beginning of the original unfragmented packet. So if the first fragment has an offset of 0, this will allow a maximum offset of 65,528 bytes, which will exceed the maximum IP packet length of 65,535 bytes with the header length included. That means plus 20 bytes extra, it means actually 65,548 bytes. The time to live field is actually one of my favorite ones. It has an 8-bit field that was created to stop packets from going into circles and creating a loop in a network. The minimum value of the TTL is 0 and the maximum is 255. We are actually using this field for a hop count. So for example, when the packet arrives at a router, the router, it will decrement the TTL field by 1. And when this field hits 0, the router simply discards the packet and sends an ICMP time exceed message to the sender. To see the time to live field in action, we can use the application traceroute to track something on the internet. First, let's see if we can reach the Google DNS server using the ping application. So as you can see, it's reachable. Okay, so we have reachability, and right now we will try to trace route to the DNS server. Oh, by the way, I used the -d over here to skip the host names. Because, for example, if you're not using -d, instead of giving you the IP address, it will actually give you the names. So this one is my firewall, this one is my router from my ISP. Over here we have a public IP, and then we have another private IP, which is like really weird. Okay, let's try to trace route. Okay, it recovered, but anyway, that felt strange. When you're using traceroute, you actually have set into the application of a maximum of 255. That means 255 hops that you can go through. We went over here on 11 hops, so like this one is the last one. So for example, from my PC it reached my firewall, and then this was the router given to me by my ISP, and then we have public interface, some from my ISP probably, and then we are going to an IP address, to a private IP address, which is like really weird. Over here we cannot see anything. We have request timeout. Most probably this is happening because of a firewall which blocked the traffic, and so on until we reach the DNS from Google. The packet left with a TTL of 255. When it reached my firewall, that TTL from 255, it was decreased by 1, which means 254. And then it got to my router, which had a 254 value, and of course that one was decreased by 1, and so on until when it got to the DNS server. After the TTL we have the protocol field. This field actually defines which kind of protocol it is used into the data portion of the IP packet. That means when the IP header it will gonna get stripped, we will gonna have decapsulation. This here is the encapsulation concept, and if we will gonna have the decapsulation going on, we will gonna start by stripping the IP packet, and then it will go to the transport layer. So depending on the value of the protocol, at the transport layer we can have, for example, a TCP header, or an UDP header, or something else. Like for example RTP, which is a protocol used for the routing protocol of EIGRP, but we will going to talk more about EIGRP in ICND2. Depending on this value, as I've said to you, this will tell which kind of layer 4 protocol should handle the segment after the IPv4 header is stripped. These numbers are given by the IANA, the Internet Assigned Numbers Authority, which maintains a list of these IP protocols. In case you want to find all the list of the protocols, you can search it on the web, something like IANA IPv4 header protocol numbers. Let's try this way. So we found them. Over here you can see, for example, the code for ICMP, the code for IGMP. Then you have the number for IPv4 encapsulation, the TCP, the transmission control protocol, has a value of 6. The UDP, user datagram protocol, has a value of 17. And so on. I have made you a list of the most common ones, except IGMP. You're gonna meet with all of them in your CCNA study. The header checksum is actually used for error checking of the header. It's 16-bit long. If you have an IP packet which arrives to a router, the router will try to calculate the checksum of the header, and it will compare it to the header checksum field. In case this value will not gonna match, the router will discard the packet, thinking that there was an error, for example, or the packet was tampered. Another thing that you need to be aware about it is that when the packet arrives to the router will decrease the TTL. So in this case, the router will calculate a new checksum and send the packet further. The source IP address is 32 bits long, the same as the destination IP address. And the source IP address belongs to the computer that is sending the packet, and the destination IP address belongs to the computer which will receive the packet. The last field in the IPv4 header are the options, and as I've said before, please remember, if the internet header length will have a value of 6, that means bigger than 5, this field will gonna be used. If the value of the internet header length will gonna have, it will be 5, that means that you're not gonna have, that this field will not gonna be used. So most of the time it's empty. But sometimes for network testing, debugging, security, and more advanced features, it can be used.